Hi there. I want to go over some chemical calculations today. I'm reviewing the first half of general chemistry, the first semester general chemistry, and so I want to start with some general comments about calculations, and then we'll do some example calculations. So the first thing is I would remind everyone of what I consider to be the two basic rules of algebra. One is that anything divided by itself is equal to 1. And the second rule is be fair. And that concludes the rules of algebra there. Obviously, there's a lot of other details, but anything divided by itself being 1 is something we use an awful lot, particularly when the two anythings don't look the same. You know, for example, 1 foot is 12 inches, which means that if I have 1 foot over 12 inches, or 12 inches over 1 foot, those are both conceptually equal to 1. And if we want to apply either one of these two things, which we call conversion factors, to an equation, we can do that on one side and still be fair because we're multiplying the other side by 1, which of course doesn't change it at all. So a lot of what you're doing in chemical calculations at this level is you're recognizing what these conversion factors are, you're recognizing where we can get those conversion factors from, and applying them correctly. So if we have something like a reaction like this, 2CO plus O2 goes to 2CO2, that tells me that 2 moles of CO are equal to 1 mole of O2, which are equal to 2 moles of CO in terms of just this reaction. And of course, that gives us a lot of conversion factors. 2 moles CO over 1 mole O2. 1 mole O2 over 2 moles CO, and 2 moles CO2 over 2 moles CO. And let's see, I believe we have some other ones. We still have 1 mole O2 over 2 moles CO. Wait a minute, I've already done that one. So maybe I should do this as 2 moles CO2 on that one, and 2 moles CO2 over 1 mole O2, and 2 moles CO over 2 moles CO2. Those don't look much different maybe, but there are subtle differences there. And of course in chemistry we're paying attention to the number, the unit, and the substance. All of those things matter and can be manipulated algebraically. We also have other relationships we know about. We know that there's 28 grams of CO and 1 mole of CO, and we know that that's 6.02 times 10 to the 23rd CO molecules. And we know since C is present, 1 C is there and 1 O is there, that's 6.02 times 10 to the 23rd C atoms, and 6.02 times 10 to the 23rd O atoms in this case. And from each of those equal signs arise a whole bunch of conversion factors. Knowing which ones are the right ones to use, again, is largely a matter of paying attention to the units and practice. And I would say one of the things that probably one of the top misconceptions in chemical calculations among students is they attempt to apply Avogadro's number, that's 6.02 times 10 to the 23rd, in many situations where you don't need to apply it. That's one thing. Another problem you see sometimes is you'll go in a circle, you'll convert grams of CO to moles of CO, and then convert it back to grams of CO because you don't really understand where you're trying to go with it. All that kind of Should be worked out with practice, but if you feel yourself going in circles, you might recognize that maybe you need to think about trying something different. And again, generally speaking, on working problems like this, I recommend getting a great big pad of paper, or get scrap paper or something, an eraser, although I wouldn't use the eraser much, pencil and your calculator, and then start trying to work the problem. Use as much paper as you need, because paper is the cheapest thing in terms of your educational expenses. And if you think something's wrong, maybe draw one line through it. Don't eradicate it, don't erase it, but draw one line through it and then maybe try again. You might find that you go back, you're actually going the right way at first. There's a lot of trial and error type stuff that goes on in doing these problems, but with practice, you will learn how to do these things. The other thing I just put here in my little bitty space I saved here is I encourage estimation before you calculate. Don't always do that myself, but generally you'll see me do that. That way I'm much better idea of whether my answer on my calculator is right or not. If I have a difference, then I can look and see whether I did something wrong in the calculation or made a mistake in the estimation, which is usually what more common type thing that happens. But anyway, so what I did was I went to your textbook, the OpenStax chemistry textbook, and I looked at chapters 1 through 9, and I went through and I tried to pull out a selection of what I was shooting for was more difficult problems from the end of the chapter. Of course, if you look at the problems back there, many of them have a blue number instead of a black one like you see here. That means the answer is available for you. And then I thought running through these and demonstrating these might give you a little reminder of the range of some of the problems that you're responsible for as we're reviewing Chem 131. All right, so mercury content. Mercury, of course, is symbol is Hg. Of a stream was believed to be above the minimum considered safe 1 part per billion by weight. An analysis indicated that the concentration was 0.68 parts per billion, which would be less than 1 part per billion, of course. What quality of mercury in grams was present in 15 liters of the water, the density of which is 0.998 grams per milliliter? Okay, and then we're also told that the definition of 1 part per billion is 1 nanogram of mercury for every gram of water. So that's kind of a useful, helpful information there. The parts per billion generally is part over whole times 10 to the 9th parts per billion, where 10 to the 9th is a billion, of course, and the part and the whole would be in the same unit. So grams of mercury over grams of water there. All right, so what we know is we got 0.68 parts per billion, which means that we can create a conversion factor based on this. So 0.68 ppb is going to be 0.68 Ng Hg, nanograms of mercury, over 1 gram of H2O. So we're just, by analogy with this, we're converting that, using that 0.68 ppb, changing the nanogram mass from 1 to 0.68, and keeping the 1 gram of water there. So what are we being asked? We're being asked what quantity of mercury is in grams of mercury. So X grams of mercury is the quantity of mercury. And what's it in? Well, it's in 15 liters of water. And, or a 15-liter solution, I would say, of water with small quantity of mercury dissolved in it. We're given a density, and but the density is in milliliters, so we're going to have to get liters into milliliters. So 1 liter is 1,000 milliliters, so liters will cancel out. And then I could say that there's 0.998 grams, and I'm going to say SOLN for solution here, over 1 milliliter of solution. And again, this 15 liters was of the solution. So milliliters is canceling out, and we have, at that point, we'd have grams of solution. Now, I haven't done any of the math yet, but all the divisions are 1, so I have 15 times 1,000, that's 15,000, times 0.998, that's just about 15,000, a little less. Now, we are told that if we have 1 gram of the water, I'm going to call that the solution actually, 1 gram of solution, it's got 0.68 nanograms of mercury. Let me just explain the solution water distinction there. So the solution is mostly water, right? There's very little mercury in it. Doesn't take much mercury to be bad, so we're worried about small amounts of mercury in it. But the solution is water. They've used water here as their term for what they should have said solution. That if you have 1 nanogram of mercury in 1 gram of solution is really what they should have said instead of water. So I'm sticking with that distinction there. So anyway, so grams of solution and grams of solution cancel out, and so now our 15,000, that's a little less than 15,000, I just multiplied by 0.68, so that's about 2/3 of that, so it's going to be around 10,000. And then I've got to deal with nanograms. All right, so 1 nanogram is 10 to the negative 9 grams. So 10,000 is 10 to the 4th, I believe, right? So 10, 100, 1,000, 10,000, it's 10 to the 4th. So if we had 10 to the 4th times 10 to the negative 9th, my estimate's going to be something around 10, let's say 10 to the 4th times 10 to the negative 9th. That's going to be 10 to the negative 5th. So my ballpark value is going to be around 10 to the negative 5th. That's 0.00001. If I get something close to that, I'll feel pretty good about it. So I'm getting the calculator out here. I've got 15 times 1,000 times 0.998 times 0.68, and then times, the way I'm going to enter 10 to the negative 9th on this TI-84 is I'm going to say 1 second, comma, that's the EE function, negative 9, and I get 1.017, so maybe 1.02 times 10 to the negative 5th grams of mercury. We have, really we only have 2 sig figs here at this point, so I would say probably to 2 sig figs 1 times 10 to the negative 5th grams of mercury would be my answer. That's negative 5th, not positive 5th. All right, so pulled an example from chapter 2 here. We got a 55 gram serving of a particular cereal that supplies 270 milligrams of sodium, which is 11% of the recommended daily allowance of sodium. How many moles and atoms of sodium are in the recommended daily allowance? So the first thing we got to do is we got to figure out how many grams of sodium are in that recommended daily allowance, right? And so we know that 270 milligrams is 11%. So how do we write that? Well, 100% on the top here and 11% on the bottom. That's 100% of the RDA and 11% of it. That's a conversion factor I'm making based on that being the recommended, that amount being 11% of the recommended daily allowance. So this is a weird conversion factor because top and bottom units will cancel out, but we'll still have milligrams. So let's see. Well, let's get rid of milligrams. We'll put 1 gram on top, and that's 1,000 milligrams on the bottom. I could have said 10 to the negative 3 grams over 1 milligram would probably be a more consistent way of doing it. So let's, estimate. 270, 100 over 11 is going to be about 9, right? So 270 times 9, well, it's going to be 300 times 9. 300 times 9, 3 times 9 is going to be 27. So it'd be like 2,700. 2,700 minus 10% would be 270, because 30 is 10% of 300. So I estimate that as 30, then I'm going to subtract 10% off of that. So 2,700 minus 270 is going to be 2,540. So I'm thinking something around 25 for my answer. So let's see here, 270 times 100 times, well, 1, didn't really need that, divided by, okay, I'm going to put in parens, 11 times 1,000. Oh, that's 1,000. Maybe it's going to be more like 25, or 2.545, yeah. So 2.45 grams of sodium is the RDA. Now, we want to know how many moles. Well, how many moles of sodium are in that 2.45 grams of sodium are the, that'd be 2,450 milligrams. If you check a table of recommended daily allowances. And so to get the molar mass of sodium, we're going to go to the periodic table. It's basically 23 grams of sodium is 1 mole. So that's going to give us 2.45 divided by 23. That's going to be a little more than 0.1. And I get 0.107 moles. So that's one answer right there. And then to get atoms, I'm going to take this and multiply it by 6.02 times 10 to the 23rd atoms per 1 mole. And so that's going to be something around 6 times 10 to the 22nd when I'm done. So 6 second, comma, to do the exponent 23. It's positive exponent, not negative 1. I always get those things wrong. And I wind up with 6.4 times 10 to the 22nd atoms. So that would be one answer. This 0.017 moles is the other answer there. All right, so going on to chapter 3, which is the chapter where we talk about light a little bit, and then get into talking about atomic structure. So not too many quantitative problems here, but there are a few associated with light, and I thought this one was one that was worth looking at. So, species, different species have eyes that are different, that see in different frequencies and wavelength of light. So reptiles, according to this, has get a single visual signal to the brain when the visual receptors are struck by photons of a wavelength of 850 nanometers. Just for reference, what we consider visible light for us is 400 to 700 nanometers. So that would be outside of our range of vision. The 850 nanometers is a longer wavelength, so it's going to be lower energy. It's probably going to be in the IR, which, I've always heard about snakes sensing heat. The IR is where you might do that. So we have a limit here on the energy, and then we're asked to get figure out the photons that we need to strike the receptor. So what do we know about photons? Well, the energy of a photon, according to Planck, is equal to h nu, which is the frequency, and we don't usually say that, but that is the energy of a single photon. And nu is c over lambda, so hc over lambda, where c is the speed of light, lambda is the wavelength, and h is Planck's constant. So the energy for that single photon at 850 is going to be Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, times the speed of light, which is 2.998, times 10 to the positive 8 meters per second. And then we're dividing that by 850 nanometers, but what we're going to do is instead of saying nanometers, we're going to say times 10 to the negative 9th meters. That's essentially equivalent to that right there is nanometers. Just a shortcut way of doing it. It's not a legit scientific notation thing to say 850 times 10 to the negative 9th, but we can put that in our calculator and it'll work. The reason we do that is that this meters and that meters cancel out, this seconds and that seconds cancel out, and we get energy in joules, which makes sense, right? All right, so let's see what we get. So I got 10 to the negative 34, 10 to the 8th, and then I'm dividing by 10 to the negative 9th. So 10 to the 8th divided by 10 to the negative 9th is going to be 8 minus negative 9 will be the exponent. So that's 8 plus 9 is going to be 10 to the 17th. And then 10 to the 17th times 10 to the negative 34th should be 10 to the negative 17th. And then looking at the rest of the numbers there, I've got basically 6.5 times 3. That's about 20. And then 20 divided by 850 is going to be a much smaller number, right? So 20 divided by 850 is going to be, it's not going to be 0.1, it's going to be something around 0.0, maybe 0.05, 0.04, something like that. So 0.04 times 10 to the negative 17th, 0.04 times 10 to the negative 17th. This is my estimate again. That's then going to be equal to, if I move this guy over twice, I reduce this, I'm multiplying that by 100, so I got to divide this by 100, so it's 4 times 10 to the negative 19th is my estimate, right, for that. And of course I could have blown something there, but at least we got something to work with. Alright, so let's do Planck's constant. We'll punch this in the calculator. 6.626 second, comma, negative sign 34 times 2. Oops, wrong button. Go backspace here. 2.998 second EE positive 8. Don't have to put the positive in. Then I'm going to divide that by 850 second, comma, that's EE, negative 9, and hit enter. And I wind up with 2.33 or 2.34, really, I guess if I round it, times 10 to the negative 19th joules. So order of magnitude's good, 10 to the negative 19 is good, 4 versus 2.34, that's the other parts of the numbers. I'm less concerned about that, but I'm pretty happy with that. All right, now this is 4.1 photon. And that's, again, something they never seem to tell you. So what we have here, how many photons are what we're being asked. How many photons have to actually hit to set the trigger off to let it know? Well, that means we've got to have 3.15 times 10 to the negative 14th joules. And what we know is that one photon gives us 2.34 times 10 to the negative 19th joules. That's what we do, is construct that conversion factor from the previous problem. So 10 to the negative 14th divided by 10 to the negative 19th is going to be 10 to the 5th, and that's 3 divided by 2 is going to be about 1.5. So I'm thinking 1.5 times 10 to the 5th is my estimate here. That's 15,000 photons. Let's see what we get. So 3.15 second, comma, negative 14, and I'm going to divide by, and on the TI-84 I could just hit second answer and pull that number down from above, and I'm off by a factor of 10. I get this comes out to be 130. I'm going to call it 135,000 photons. It's of course the number has more non-zero numbers than that, but I'm rounding it off at 3 sig figs there as 135,000 photons. So somehow I was off by a factor of 10 there, or I typed something in wrong. Okay, I think I'm okay. I can live with that one. All right. Next up now, so Chapter 4, Chapter 5 are both very structural, and we'll talk about those a little bit more, and that'll even carry over into our first unit after we do this review unit. Let's look at going to Chapter 6, which is where we start talking about a bunch of chemical calculations there. There's a few examples that I thought would be worth going over. Again, there are lots of different kinds of problems like this, and I'm not going to hit every single type of problem, but let's hit some of the high points. So we're told here that a compound called dichloroethane, which is used for dry cleaning, contains carbon, hydrogen, and chlorine. Now what that tells me is that this formula, which I've read ahead, I see that it's asking me the formula. The formula is going to be something, C sub x, H sub y, Cl sub z. Our job is to figure out what x, y, and z are here. You know, we're asked what's the molecular formula. We're told that its molar mass is 99 grams per mole, so that's going to help us in a little bit here. Analysis of the sample show that it contains 24.3% carbon and 4.1% hydrogen. That's the information we're going to start off with. So, to solve this problem, first thing we got to do is say, okay, what's the percent chlorine, right? Well, if all I have is carbon, hydrogen, and chlorine, then if I add those percentages up, they better be 100%. And if I subtract my 24.3% carbon and our 4.1% hydrogen from the total of 100%, that's going to give me the percent chlorine, which is actually going to be quite a bit. So 100 minus 24.3 plus 4.1, that's all in the parentheses, which is why I said minus parentheses 24.3 plus 4.1 close parentheses. So that should that's going to be 28.2 inside the parentheses. So the rest of it's going to be 81.8, I think. 71.6. 71.6. Yeah, you're right. Okay, that's 71.6% chlorine. Yeah, that makes sense. All right, so let's look at our what we're going to do next in this problem is we're going to assume 100 grams of the compound. Now, CPD is the compound. If I do that, the reason I pick 100 grams is it makes it easy. 24.3 grams of that are carbon, 4.1 grams of that are hydrogen, and 71.6 grams of that are chlorine. So what we're going to do now is convert those to moles. So the chlorine will be 1 mole of chlorine, and if you look on the periodic table, chlorine is 35.453 grams of chlorine in 1 mole. Oftentimes just shortcut that as 35.5, but certainly never rounded to 35 or 36. Grams of chlorine will cancel out, and that looks like it's going to be right around 2. Yeah, that comes out to 2.02 moles of chlorine. 4.1 grams of hydrogen rather, 1 mole of hydrogen is basically 1.01 grams of hydrogen, and again, 1 is usually good enough for that. That comes out to be 4.06 moles of hydrogen, and then carbon, I'm going to say 1 mole of carbon is 12.01 grams of carbon. Again, getting that from the periodic table. So that looks like 24.3 divided by 12.01. That comes out to be 2.02 moles of carbon. So then I write the equation, my formula, C sub 2.02, H sub 4.06, Cl sub 2.02, and then I divide each one of these by the lowest number. Well, that's 2.02 is a tie in both cases. And what that does is that sets the lowest one to 1. So I have C1, H is going to be 4.06 divided by 2.02. That's 2.01, so basically 2. And Cl is going to be 1. Now, we're told that the molar mass, this would be what we call the empirical formula. Okay, the molar mass is we're told is 99 grams per mole. The empirical formula mass, which is the molar mass of the empirical formula, so I'm going to have 12 plus 1 plus 35.5 for 12 plus 2. So that's my carbon, my hydrogen, I got 2 of them, and I got my 1 chlorine there. So 12 plus 2 plus 35.5, that's going to be 49.5. Okay, so if I take my molar mass and I divide it by my empirical formula mass, that's going to be 99 divided by 49.5, and that is going to come out to 2. That's our multiplier. So our molecular formula is going to be C2, 1 times 2, H4, 2 times 2, Cl2, 1 times 2. So it's 2 of those empirical formulas to make the molecular formula for that. So that's an example of what we call formula stoichiometry. Again, in this case, we were given percentages, which we converted to grams by assuming 100 grams. Some other times you might be given actual grams, or you might be given chemical data that lets you get back to the number of grams. The basic idea, though, is you're figuring out how many moles are present, looking at that mole ratio to get your formula, and then if you're given a molar mass, you can use the ratio of the molar mass to the empirical formula mass to see how much you multiply that empirical formula by to get the actual molecular formula. All right, next question is kind of a classic. It is one that the answer is in the book because it's in blue. I was trying to pick the black ones there, but you see that little blue thing there tells you that the answer is in the back of the book. I think you just click on the number actually to get it. But this is a classic. You're told that you have a concentrated solution of nitric acid, which is 68% nitric acid by mass. And, well, actually, this is not the classic one. We're asked what mass of that is needed to prepare 400 grams of a 10% solution of nitric acid by mass. So, what are we trying to figure out? We're trying to figure out the mass of the concentrated solution. So I'm going to say CONC. I'm not even going to put nitric acid there. I'm just going to say CONC for concentrated solution is equal to 400 grams of, I'm going to say DIL for the dilute solution. So this is the concentrated, and this is dilute. And that's just a relative term. Dilute means less concentrated. In this case, we're looking at a concentrated and a dilute solution. Now, we know that we have a 10% solution of nitric acid by mass, which tells us that if I have 100 grams of my dilute solution, how many grams of it are actually nitric acid? And the 10% tells us that that's 10 grams. And we know that out to 3 sig figs. So that's, again, the dilute solution. So grams of dilute and grams of dilute will cancel out. And again, that percentage there gave us this conversion factor. Now, next up, we're going to need to go from grams of nitric acid to grams of concentrated. So we're going to use this percentage now, and now if I have 100 grams of the concentrated solution, it's going to contain 68 grams of nitric acid. And so that should give me the answer in terms of how many grams of the concentrated solution I need. All right, so we have 400, 100 and 100, we can cancel those out. That's easy enough. 400 times 10 is 4,000. 4,000 divided by 68. Okay. 4,000 divided by 50 would be what? That's there's 20 50s and 1,000, so 80. So I think it's going to be a little less than 80, but not too much less than 80. How's that for an estimate? So this is what I call parameterizing. So my estimate is less than 80. So 400 times 10 divided by 68 equals 58.8 grams of the concentrated HNO3. So that meets my less than 80 criterion, so I'm pretty happy with that one. Again, two tricks there is we're creating our conversion factor from percents. We're juggling the fact that we have a concentrated solution and a dilute solution. Both of those we can relate to amounts of nitric acid, but they're both different. And then, of course, this one always, what am I being asked? What mass of concentrated told me this? And then I start with the only other thing that isn't a conversion factor here, the 400 grams that we started with. All right, so going into chapter 7 here, we have a problem that is a stoichiometry problem. And we're told that I2 is produced by the reaction of 0.4235 moles of copper chloride according to this following equation. We're asked how many moles or how many molecules of I2 and what mass of I2 is produced. So first of all, we have to read this, and there's something they didn't say here, but what they imply by not saying it is that we have excess Ki. Since they didn't give an amount of Ki, that assumes that we've got enough Ki that's not going to be an issue. It's going to be the copper chloride that runs out first. Of course, a lot of times we shortcut excess and just write it as XS, which makes too much sense. But you need to know that. All right, so we're asked how many molecules and what mass of I2 are produced. What I'm going to do is I'm going to start my calculation out. I'm going to say X, and I'm going to put blank there I2, because I don't want to do it twice, and we can get both of them from this. So, all right, so we know we got 0.4235, and I left the 2 out. And again, that's the kind of mistake that would give me a wrong answer if I didn't catch it. 4.335 moles of copper chloride. Now, that is reacting to produce I2, 1 mole of I2, that 1 comes from that invisible 1 there, reacts with 2 moles of our copper chloride. And that 2 there is the 2 that we have down here. Moles of copper chloride cancel out. Now, at that point, I've got moles of I2. I can go take that number one way and say that 1 mole of I2 has 6.02 times 10 to the 23rd I2 molecules. And we have to be clear that they're asking us molecules and not atoms. Atoms would be twice as many in this case. Or we could say that 1 mole of I2 is going to be how many grams of I2 is that. I don't have a periodic table laying around right here. Let's just go back over here. I'm going to look back in the General Info tab. And on this, I can go down here and look and see the periodic table, which is sideways, unfortunately. But that looks like 126.9, basically 127. So I'll go back to review of Chem 121. So 127 times 2, that's going to be 254 grams of I2. And so that'll give me grams of I2. That one will give me molecules of I2. So let's run it. 0.4235 divided by 2. Yeah, I messed it up. I accidentally put negative signs in. Trying to hit enter, I hit the negative sign twice. And turns out I had hit the multiply sign, not the divide sign there. So 4235 divided by 2, it's going to be about 2.1, right? So this number here, this would be 0.21175 moles of I2 at that point. If I multiply that times Avogadro's number, 6.02, second, comma, 23, and that's 1. Get a little more room over here. So, oh yeah, expand the thing back, sorry. All right, that's going to be 1.275 times 10 to the 23rd molecules, which of course you'd expect it to be a lot of molecules. And then if I take that 0.21175 and instead multiply it by the 254 grams per mole, that's going to get me 53.78 grams of I2 to do 4 sig figs. So that's one answer. That's the other. I guess you can check me in the back of the book, see if I got that one right. No, that's not the one that had the right answer. Sorry about that. Guess you got to trust me on that one. But those look like reasonable answers. All right, so we used formula stoichiometry there. We used Avogadro's number, and we used the molar mass as well. All right, so next up here, excuse my copy of the problem there kind of grabbed just half of the sentence of the next one. We've got another reaction. Calcium carbonate is decomposing into calcium oxide and CO2. And what we're told is that we got 0.53 grams of carbon dioxide from heating the 1.31 grams of calcium carbonate. What is the percent yield? So we got to think about a couple of formulas here. What's percent yield? Percent yield is the actual yield over the theoretical yield times 100%. Now, we're trying to get the percent yield. The actual yield is given to us, this 0.53 grams here. That is our actual yield. What we have to do is figure out what the theoretical yield is, which is going to be grams of carbon dioxide as well. We've got to have theoretical yield in the same units and substance as the one we're comparing it to the actual yield. So we'll start off with our 1.31 grams of calcium carbonate, and our first step will be to convert that to moles. So 1 mole of calcium carbonate. Okay, let's think about this. So CaCO3. Calcium has a molar mass of about 40. Carbon has 12. 3 oxygens are 48. You get to know your 16s table pretty quickly if you're a chemist. And so lo and behold, that actually adds up to 100. 100 grams of CaCO3. So at this point, we're canceling out grams of CaCO3, and that's of course why we chose to arrange that second conversion factor that way, so that it does cancel out grams of CaCO3. Our middle conversion factor here, we're going to have moles of CaCO3 on the bottom. And we're trying to go over to CO2 now, so we'll have moles of CO2. We're going to get those numbers from the coefficients in the equation, and both of them have no coefficient written, which means that they are 1 to 1. So that lets me cancel out moles of CaCO3, but there's nothing there mathematically I have to do. And then finally, in the last step, we need to go from moles of CO2 to grams of CO2. Now, when you're doing these molar mass things, you're always going to have 1 mole. There's an instinct sometimes to take whatever number is on the top of the middle coefficient there and drop it down to the bottom here, which would work in this case. But generally speaking, the top of your conversion factor has to be equal to the bottom of your conversion factor. 1 mole is 44 grams of CO2, and that's one of the things you might check as you're looking at your conversion factors, and make sure that the top's equal to the bottom. 1 mole of calcium carbonate is 100 grams. 1 mole of CO2 is 1 mole of CaCO3 according to this reaction. 44 grams is 1 mole of CO2 according to the periodic table in the formula. All right, so we got 1.31 times 44 divided by 100, so that's going to be about 4/10 of 1.31, so I'm gonna 0.4, I think it's gonna be around 0.5, 0.6 is my estimate. So I'll write up here my estimate, 0.5 to 0.6. So let's see what we got here. So 1.31 divided by 100, I'll hit enter, times 44, leave out all those ones, and I get 0.576 grams of CO2. That again is my theoretical yield. So my percent yield is now going to be my actual yield. That's my 0.53 grams over my theoretical yield, which is 0.576. Oops, left the 5 out. 0.576 grams So the other end of the thing is 4.576 grams. Those are both of CO2 times 100%. So we're pretty close to 100% yield here. We're down by about 0.4, 0.5. So I think it's going to be a little north of 90%, but not much off of that. So I'm going to say 0.53 divided by second answer, because I have the 0.576 in there above that, and then multiply that by 100, and I get 91.9%, or I'd have to say, I guess, 92%, based on 2 sig figs and the 0.53 grams. So that would be my percent yield, 92%. Very important calculation. You'll do those in organic lab routinely. And okay, here's another problem. We've got KHP, or potassium hydrogen phthalate, which we use a lot of times to standardize bases. And we have a reaction here where a 0.3420 gram sample of potassium phthalate reacts with 35.73 milliliters of a NaOH solution in titration. What is the molar concentration of NaOH? Okay, so we want to know the molar concentration. Molarity of NaOH is going to be moles of NaOH over liters of NaOH solution. And we know that when we actually, this 35.73 milliliters is going to be our volume there. So that's going to be 35.73 milliliters times 1 liter over 1,000 milliliters. That's pretty easy. We just move that decimal point over, so 0.03573 liters. So we know what the number on the bottom is pretty quickly. Now what we have to do is figure out how much NaOH. So what we want is moles of NaOH is equal to our 0.3420 grams of our KHP. Now, I have a memory of KHB having a molar mass of 204.3 grams of KHP for every 1 mole. Now, let's just check that. So we have K, H, C8, H5, O4. K is 39, H is 1. 8 times 12 is 96. 5 times 1, that's 5. And 4 times 16 is 64. So 6 and 4 is 10, 9 and 1 is 10. So I'm going to be carrying my 2, and I have a 5 here. 6 and 9 is 5, so it gets give about 205. And so I would assume that if I rounded that off correctly, my 204.3 is pretty close. So I'm going to go with what I remember. But you might have used 205. I don't think I messed any of those up. All right. Other good news here is the conversion factors again are 1 to 1. We've got 1 mole of the KHP, which again, KHP is this thing right here. And that reacts with 1 mole of NaOH. So we cancel out grams of KHP, cancel out moles of KHP, we're good. So 0.3420 divided by 204.3, that's going to be pretty small. If this were 0.204, that would be 0.0001. So my estimate's going to be 0.0015. So that's my estimate for this one. Again, might be somewhere around that range, and it's always easy to blow a decimal point one way or the other on these. So 0.3420 divided by 204.3. That's 0.01. 0.001. Guess I'll carry it on out. 674 moles. So pretty close to my estimate. So then my molarity is going to be 0.001674 moles divided by 0.03573 liters. So I've got the mole number in my calculator. I just hit divide 0.03573. Copy that right. Yep. And that comes out to be a molarity of 0.04685 molar is, I think, what we can claim is a correct answer for that one. All right, so that's formula stoichiometry, or sorry, that's reaction stoichiometry with the volumes involved, volumetric analysis it might be called. All right, 34 takes us into Chapter 8, which is about the gas laws. We're given some iodine. It sublimes into a gas, and we have a bulb that has a volume of 73.3 milliliters. It contains 0.292 grams of iodine vapor, and we know the pressure is 0.462 atmospheres. We're asked what's the temperature. So the ideal gas equation is PV equals nRT. And we're going to solve that equation for the thing we're asked for, the temperature. So temperature is going to be equal to PV divided by NR. So the pressure is 0.462 atms. The volume, we're going to want the volume in liters, so that's going to be 0.0733 liters if you do that conversion. We've got to calculate moles. So how many moles of I2 do we have? That's the same thing as saying X moles of I2, N of I2. We've got 0.292 grams of I2, and we're going to multiply by 1 mole over the molar mass of I2. And I feel like we used that just a little bit earlier. Let's look up here. Is that 254? Yeah, right there. We just used it right there. We called it 254. So that's handy. I'll just write that again here, 254 grams of I2. So 0.292 divided by 254, that comes out to be 0.00115 moles of I2 basically. So we'd say 0.00115. Now, I've got that number in my calculator. I'm going to use it with all the sig figs that are all the decimal points it gave me, and then we'll round at the end. That's what you normally do, but that, if I had to round it right there, that's what it would be. And then R. R is, let's see, if I don't remember R, it's always easy to get confused. I think I know it, but let's go look here on the formula sheets and find R. And the molar gas constant here, we have two values up here. We're going to use the one with liters, atmospheres, moles, and kelvins. So 0.08206. So 0.08206, that's liters times atmospheres over moles times Kelvin. All right, so atmospheres and atmospheres will cancel out. Liters and liters will cancel out. Moles and moles will cancel out. We have 1 over, unit-wise, we got no units on the top, so we'll call it 1. Then on the bottom, the only thing we have is kelvins, which is also on the bottom. So 1 over kelvins, and 1 over kelvins is going to be equal to 1 times kelvins over 1. Essentially, this is 1 over 1 divided by 1 over kelvins. That comes out to be kelvins. So we'll get a temperature in kelvins here. It didn't ask us what temperature, what units to get temperature in, so kelvins are good. All right, so I've got 0.462 times 0.0733. Yeah, I'm not going to estimate that one. Divided by parentheses. All right, I'm going to pull the mole thing in here with the second answer. So that's the 0.00115. And I've got that in a parenthesis, so I can just multiply the other bottom term, 0.08206, close the paren, and I get 359 Kelvin Is that a reasonable sort of temperature? Well, in Celsius, I would subtract 273 from that. That would be 86 Celsius, basically, which is going to be pretty warm. But the bulb, we may have been heating the bulb so that it was pretty warm. 86 Celsius, it's around the boiling point of ethanol, for example, a little above it. So not an unheard of temperature in a lab. All right. So we have here a gas mixture problem, and the gas mixture problem is one where we collected a sample of this gas over water. The volume of the gas was 265 milliliters at pressure of 753 torr and temperature of 27. We're given the mass of the gas. We're asked the molar mass of the gas. So the first thing we have to do is recognize what this collecting the sample over water means. What that means is that we have a mixture. We have a mixture of our total pressure is going to be the sum of the pressure of our gas, which we don't know what the gas is, so I'm going to say piece of gas, plus the partial pressure due to water. As you bubble the gas through the water, it picks up water vapor, and that is totally dependent on the temperature. So if I go to this table, which I copied from the textbook here, this gets me the value for the vapor pressure of the water in torr. So it's 26.7. So we had 753 torr as our total pressure, and that's equal to the pressure of the gas plus that 26.7 torr. This is torr. So again, this is my total pressure. So my pressure of my gas is actually 753 minus 26.7 torr. So that's going to be something in the 753 minus 26.7, 726.3 torr is our corrected pressure for the gas. Now, what else do we know about the gas? Well, if you look on the formula sheet, there is an equation here that's given. Right here you see the molar mass is in this equation. This is from the ideal gas equation. It also talks about density there. It comes from taking this equation and plugging N is equal to M over molar mass, script M, into this, and we get that equation. So M over V, little m over V, is equal to P molar mass over RT. So from that equation sheet, we know that little m over V equals to P molar mass over RT. So this is our equation we're going to try to solve and with the data that we have. So let's rearrange that. Molar mass is going to be equal to MRT over PV. So what do we have here? We know that the mass is 0.472 grams. We know that the gas constant is 0.08206 liters times atmospheres over moles times Kelvin. We know the temperature is 27 Celsius, so 27 Celsius plus 273 is 300 Kelvin, nice round number. So this is the temperature is 300 Kelvin, which I'm going to have to draw in up here above it. And then on the bottom, my pressure now, I got a Torricelli, I need to get it in atmospheres, so the P, if I multiply this by 1 atm over 760 torr, which is the conversion factor for that, I get my pressure of my gas is going to be about 0.9 or so, 0.956. So I'll say 0.956 atm. So down here I have 0.956 atm. And then the volume was given to us, it was 265 milliliters, which means that that's 0.265 liters. So 0.265 liters. All right. So I'm going to start off by doing the bottom part. So the 0.956 times the 0.265 liters. That gives me the bottom part of that. Then I'm going to use the invert function on that, the x to the minus 1 function, and multiply it by the stuff on the top, 0.472, 0.08206, and 300 Kelvin. And that comes out to a molar mass of 45.9 grams per mole is what we get for that one. The units do work out. I don't really have room here to show you how those work out, but the units do work out for that one. Question, I thought this was a kind of a cool one. We were told that 1 molecule of hemoglobin, which of course is the respiratory protein in our bodies that carries oxygen from our lungs out to our cells. If we have 1 gram of hemoglobin and it combines with 1.53 milliliters of oxygen at body temperature, and a pressure of 743 torr, what is the molar mass of the hemoglobin? All right, so here's what we know. We know that that the ratio of hemoglobin to oxygen is going to be 4 moles of O2 for every 1 mole of hemoglobin. HB is abbreviated hemoglobin in biochemistry, so I'm going to use that for sure. So can we figure out how many moles of oxygen we had? Well, we know a volume of oxygen, we know a temperature of oxygen, we know the pressure, we can get the moles of oxygen. So our moles of oxygen, so again we got PV equals nRT, right, is our ideal gas equation. Solving that for N, that's going to be PV over RT. We're going to have to put pressure into atmosphere, so this is going to be 743 torr times 1 atm over 760 torr. So that's the pressure with the conversion built in. Our volume, we've got 1.53 milliliters, and our conversion there would be that we're going to liters, 1 liter over 1,000 milliliters. So that's the conversions on the top written out explicitly. We have got R, which is that 0.08206 liters times atmospheres over moles times Kelvin. And then our temperature is 37 Celsius plus 273. That's 310 Kelvin is human body temperature, roughly. Lots of units to play with here. Kelvin and Kelvin cancel out. Atmospheres and atmospheres cancel out. Torricelli and torricelli cancel out. Milliliters and milliliters cancel out. Liters and liters cancel out. So we've got moles on the bottom, so that'll work out to be moles on the top, which is what we expect, right? So let's see what we get here. So 743 divided by 760 times parentheses 1, that's 1.53 divided by 1,000 divided by parentheses 0.08206 times 310 close parentheses. That is 33.96 moles of oxygen, which seems like an awful lot. So yeah, I think I'm going to be checking that answer again. Let's try that again. Oh yeah, all right. I blew the pressure. I look back at this multiplication. I actually didn't do the division, so that's why it looks wrong. All right, so 743 divided by 760 is my first number. There we go. And then that times parentheses 1.53 divided by 1,000, and then that divided by the R 0.08206 in a parentheses times 310, and then close that parentheses. All right, that's a much better answer. Now we have 5.89 times 10 to the negative fifth moles of O2. I knew that that little bitty bit of oxygen couldn't be that many moles of oxygen. 1 mole of oxygen would typically occupy 22.4 liters at STP, so I knew that that was unreasonably large. All right, so that's moles of oxygen. So here's what we know. How many moles of hemoglobin must we have? Well, if I have 5.89 times 10 to the negative fifth moles of O2, and I know that for every 1 mole of hemoglobin, 4 moles of O2 absorb, so I'll just divide that by 4, and that gives me that I have 1.47 times 10 to the negative fifth moles of hemoglobin, because moles of O2 and moles of O2 cancel out. And again, that's that 4-to-1 ratio we got from the first sentence there. All right, so to get the molar mass, what we're going to do is say molar mass is mass divided by moles in this case, right? Moles are mass divided by molar mass, so work that around. Molar mass is mass divided by moles. We have 1.0 gram of hemoglobin that was given up here, and we figured out that that must be 1.47 times 10 to the negative fifth moles of hemoglobin. So that's just taking the inverse of this number, and the molar mass comes out to be 68,000, and that's as many sig figs as I should get. 68,000 grams per mole is about our molar mass. Biochemists would call this 68 kilodaltons, where the dalton is the 1 gram per mole basically, and so 68 kilodalton protein, which is a pretty reasonable answer for hemoglobin there. So kind of a cool question there. All right, just a couple more to go. I know it's going on long, but just a couple more to go. These are from the thermochemistry, chapter 9. We have an aluminum kettle that weighs 1.05 kilograms. We're going to talk about heating up this kettle. We're asked what's the heat capacity of the kettle. So I printed part of the table here. Aluminum has a specific heat of 0.897 joules per gram times degree C. So we have here 1.05 kilograms. We'll convert that to grams. 1,000 grams over 1 kilogram. And then we'll multiply that by 0.897 joules per grams times degree C, and that will give us the heat capacity of the kettle itself. If you're heating up the kettle's going to absorb heat. So we have 1.05 times 1,000 times 0.897. Kilograms cancels out, grams cancel out, and we wind up with 941.85 joules per degree C. So, if you're trying to increase the temperature of the kettle, you know, we say Q is equal to M S delta T, where S is the specific heat. M times S in this case gave us the heat capacity, which we'll call C. For an object, its Q is just equal to C delta T. Delta T here is 99 minus 23, and that's going to be 76.0 degrees C. Right? Let's try it. Check it. 99 minus 23. 76, yes, right. So we have Q is going to be 941.85 joules per degree C times the 76.0 degrees C. That's going to give us 71,576.8 joules, and again, I would probably not claim every single one of those sig figs. Maybe 3 of them, but that's the answer we'll run with for right now. Now, question C says, okay, we put 1.25 liters of water in the kettle first, and So we heat it up again. So if we think about this, what we're doing is we're taking the Q for this is going to be equal to the Q for the kettle plus the Q for the water. And the good news is the Q for the kettle was in part B. We already figured that part out. That's the 71,576.8 joules. Q for the water is going to be MS delta T. The mass of water is 1.25 liters times 1,000 milliliters per liter times 0.997 grams per milliliter. So all that right there gets me the mass of water. And then we're going to be multiplying that, carrying it around here, multiplying that by the 4.184 joules per gram times degree C times our delta T, which was 76.0 degrees C. So the Q for the water comes out to be, so 1.25 times 1,000 is 1250 milliliters of water times 0.997 is going to be just a little less than that grams of water, so 1246.25 grams of water times the 4.184 heat capacity times the 76 degrees delta T, and we wind up with that being 396,287. So that's not clear the way I read it. Sorry about that. 396,287.56 joules. Again, I wouldn't claim all those sig figs. Q for the whole thing, okay, the answer for C is going to be then 71,576.8. Oops, write that over again. 71,000, that is not a negative sign there. Let's be very clear about that. We're putting heat in. 71,577, let's just call it that, plus, we'll call this one 396,288 joules. So if we add those up, that comes out to be 467,865 joules. And realistically, I guess I would call that, I'd probably round it off at 3 sig figs, 468 kilojoules, or 468,000 joules would be an approximation of how many sig figs we could count on that one. So either one of those answers would be the right answer for that. So that's a little heating cooling curve question there, and we had to also deal with the difference between the specific heat capacity, which is the S, and the object heat capacity, which is the C. Final question, and I know you're all applauding madly. We're going to look at a calculation of an enthalpy change, which is how much heat's given off in a reaction. And we're looking at the combustion of propane, which of course is what might be in a gas grill, and combustion's reaction with oxygen to give us CO2 and H2O gas. First thing we have to do is balance the equation. So I'm going to need a 3 here initially. I'm going to need a 4 there. 3 times 2 gives me 6, plus 4, that gives me 10 oxygens, so 5 oxygens work there, so it balances out nicely. Those are my mole ratios that I'll use. If I look for these are the delta H sub F values from the table. Those are in kilojoules per mole. I don't have O2 written here because O2 is an element in standard state. Its value is going to be 0. So if I put O2 here, that would be 0. Now, which one of the H2Os do I use? It says H2O gas, so I'm going to use this value, not the one above it. So I'm going to write those over here. I don't know. Well, we do have the enthalpy formation of protein. This one's negative 104. This is 0. This one is negative 393.51. And this one is negative 241.86. and those are all kilojoules per mole. Our equation for this is that delta H for the reaction is going to be equal to the sum for the products of the moles times the number of delta H, the delta H of F values, minus the sum over the reactants of moles, which I'll call M here, times delta H sub F. So what we have here for our delta H, oops, I lied, there's another problem. Delta H for the reaction is going to be, okay, we're looking at the products first, so we have 3 for my CO2 times negative 393.51. So that's the first term in the product summation. The second one's going to be the water. That's going to be 4, and that's going to be times negative 241.82. And then we'll subtract from that 1 times negative 104. That is our propane term, and then the 5 times 0 is our oxygen term. That's going to be 0, so we're not going to worry about that too much. And again, all that's going to be in kilojoules per mole. We don't have to worry too much about carrying the units forward. All right, so I will do this, try to do it all in one line. Negative 393.51. You know, generally I would probably do these as separate, do the two big brackets separately, but for the sake of time I'll try to do everything on one line. And nice thing about it is that last thing reduces to just a single term. Alright, so I get the delta H for this reaction is negative 2251, and my negative sign doesn't look too clear there. Delta H RXN, negative 2251.81 kilojoules per mole. So don't stick your hand into the propane grill, or you will get burned. Right, a lot of heat being given off there. All right, number 90 here talks about looking at energy changes in terms of bond energies, which gives us a powerful tool to estimate things for things that we maybe don't know the structures are. So the first things it asks is to draw this curve of the way the energy of a system with H and Cl's atoms at varying distance. What that looks like is we have energy on our y-axis, we have distance on the x-axis like so, and this calls for a different color. All right, what will happen, this is the 0 value where the axis is there. What will happen is as the atoms are far, far apart, they have no interaction. As they come together, they begin to form an interaction, and then eventually the interaction starts becoming less favorable and becomes eventually prohibitively thing. You just can't squeeze the two atoms together very well. This distance right here is what we call the bond enthalpy of the bond, and what the distance that it occurs at would be the bond length. That is the common bond length for that bond. That's one of the graphs I carry around in my memory to think about. So the first thing we're asked to do is to figure out a way to calculate this for one single HCl bond. So we go and look at our table of average bond energies or enthalpies, and we need to find us our HCl bond. So there's our HCl bond. This tells us it's 432 kilojoules per mole. So 432 kilojoules per mole, and then we multiply that by 1 mole divided by Avogadro's number. I'll call it bonds in this case since it's asking us per bond. So we have 432 divided by 6.02 second, comma 23. That comes out to be 7.17. 7.17 times 10 to the negative 22 kilojoules per bond, which we probably want to at least put it in joules. So I'm going to multiply that by 1,000 to get joules, and that's 7.17 times 10 to the negative 19 joules, which, if you remember that 10 to the negative 19 number sounding familiar, let's go back and look up here. We did a calculation of the snakes getting the vision stuff, right? And that was at around 10 to the negative 19 joules, so we are getting close to things that might interact with a bond there. Might be enough energy to pop a bond away. All right, so that's the first version A there. Second version is we're supposed to calculate the bond energies given this reaction. So using the thing that we have above, we would say that delta H for this, actually what we're going to do is we're going to do delta H for our reaction is going to be approximately equal to the sum of the bond energies of bonds that are broken, the bonds that we put energy into break bonds, minus the sum of the bond energies of the bonds that we form. All right, so if we look at this reaction, we're breaking a hydrogen-hydrogen bond, and we're breaking a chlorine-chlorine bond, and then we're forming 2 times a hydrogen-chlorine bond, right? So, and that's equal to, we're already given the answer for the whole thing, it's negative 184.7. Now, if we look on our chart here, HH is 436, and CL is, I think down here, thought I had CL down here somewhere. Here we go, CL is 243. And I pulled this chart from the book, of course. And so what we have here eventually is we have this equation. We have 436 plus 243 minus 2 times X, which is the HCl bond, is equal to negative 184.7. And those are all in kilojoules per mole. So I would add 2X to both sides. I would add 184.7 to both sides. So I'll wind up with 2x over here and 436 plus 243 plus 184.7 and that's going to be x. My hydrogen chlorine bond energy is going to be equal to 436 plus 243 plus 184.7, and then dividing that by 2, 431.85 kilojoules per mole. And so that we were asked to get the energy of 1 mole, so that's an acceptable answer. Notice that's not too far off that estimated value over there, the table, the average value in the bond energies, but that's an example of doing a bond energy type calculation. We'll review these again when we get to the energetics unit, but you are responsible for them at this point in time. Okay, I know that's probably more of Chem 131 than you wanted to have today, so we will end it up here. So thanks for listening.